So this is part 2 of graphing and comparing functions. Now that we've learned how to graph different functions and lines, now we're going to be looking at how can we compare them. In this first set of problems, what we're looking at is we have a system of two equations. What we want to do is we want to graph both lines, and we want to be as accurate as possible, so have that straight edge pretty handy. So in the first equation here, we see our equation in slope-intercept form. The slope is the number right in front of this x, which is 2, and I'm going to go ahead and write it as a fraction so I can clearly see that my rise is 2, my run is 1. My y-intercept for this particular equation is going to be -3. That means on the y-axis we begin with the -3. From here, we're going to rise 2, run 1. Rise 2, run 1. Rise 2, run 1. And you can just go a few points, and then you're going to pick up that straight edge and try to get this as accurate as possible. And then I'm going to go ahead and label this line as y equals 2x minus 3 so that we can know what equation it is when we're ready to compare it. Now on the second equation in the system, notice it's not in slope-intercept form. We want to make it that way first. So we're going to bring it down, -x plus 2y equals 0. And what we want to do is we want to go ahead and solve this equation for y. So always move that x term. We see it's negative, so the opposite of a negative x is a positive x. So what we're doing is we're really adding x to both sides. These x's will cancel because -x plus x is 0. It cancels. What I have left is 2y equals, and 0 plus x, anything plus 0 is going to be that thing. So in this case, 0 plus x equals x. Now we want to get y by itself. Well, what we're going to do is we have 2y equals x. And the opposite of multiplying by this 2 is to divide both sides by 2. Now the 2's will cancel here because 2 divided by 2 is equal to 1, and 1y is equal to y. But I want to rewrite this part here of x over 2. There's an invisible 1 right next to the x. So it's like saying we have 1/2, and then we can move the x to the side. Now it's a little trickier on this one because we have to figure out what our slope is, which is the number, the coefficient in front of x, which is 1/2. But we also have to figure out what our y-intercept is. Well, if you see there's nothing there. If there's nothing there, it's plus 0, or the y-intercept is 0. So from here, we're going to plot our point, our beginning value at 0, and we're going to rise 1, run 2, rise 1, run 2, rise 1, run 2. And again, pick up that straight edge. And I'm going to go ahead and also label this equation as well as the -x plus 2y equals 0 equation. So now we're ready to compare. Well, what kind of things do we see? Well, we see that y equals 2x minus 3 has a greater rate of change. We see that both functions have the same y value when x equals, and let's see what that is. So they intersect here when x is 2, they both have a y value of 1, so when x equals 2. We could say that this equation, -x plus 2y equals 0, is decreasing at a slower rate. And so you can kind of look at these functions, and there'll be more questions that you can answer about them. But you want to look at them sometimes individually, like where we say this one's increasing at a slower rate, or collectively, where we say they intersect right here. Let's look at another example. In this example, it says which function has a greater rate of change when x equals 1. Well, when x equals 1, we're looking for a greater rate of change. You know what? Honestly, it doesn't matter what function, what x we're looking at, because when x is 1 and we're talking about a greater rate of change, this one has a rate of change of 1/2, and this one right here has a rate of change of 2. No matter what, this function right here, the y equals 2x minus 3, will continually have a greater rate of change no matter what x value we're looking at. Number 6. Number 6, at what values are the functions the same? Well, we already answered that question right here. When x equals 2, the y is equal to 1. So at the point 2, 1, our intersection point, the x value is equal to 2 when the functions are actually the same. And then finally, special equations. Y equals 2. And what you want to think about is that when you have a y equals equation, it will always be a flat equation. When you have an x equals equation, it will always be a vertical equation. So in this case, when y is 2, find out where y is 2, it's right here. The graph is going to look like a flat line right here. And then it says, name the slope and the y-intercept. Well, if you look, we rise nothing, but we run however much we want. Whenever you have a flat slope right here, we say that it has no slope, or the slope is equal to 0. Compare that to the following equation with an x equals, which is a vertical line, when x equals negative 1, right here. So notice that this is going through where x is negative 1. We want to look, what's the slope? Well, it's not a flat line, it's not no slope, it's not 0 slope. The slope is actually undefined. What that means is that there is a fraction. We could say we rise 2, run 0. That's 2 over 0. Anytime that you have a 0 in the denominator, it's undefined. And the y-intercept. The y-intercept for this particular problem is it never crosses the y-axis, so there is none. There is no y-intercept here. So let's go back to the previous question and compare that to the y-intercept on the previous question. On the previous question, where does it cross the y-axis? Well, the y-intercept is right there at 2. So we can have a y-intercept when we have a y equals a number line, but we would have no slope or 0 slope, versus if it's a vertical line and x equals a number line, the slope will always be undefined, and we have a y-intercept of none because it's not going to cross this y-axis.